Section. Introduction. Let's dive into the fascinating world of common sense reasoning, a key aspect of human cognition that helps us navigate the complexities of daily life. Imagine deciding what to wear based on the weather. This decision isn't just about picking an outfit. It involves understanding weather patterns, the appropriateness of different clothes for varying temperatures, and the social context of the occasion. It's about piecing together different bits of knowledge. A forecast predicting rain, the practical need for a raincoat, and the societal expectation of dressing suitably for an event. This reasoning isn't just about processing information. It's about integrating various pieces of knowledge that we humans often take for granted. In the field of natural language processing, NLP, a significant challenge is the ambiguity and underspecification of human language. We humans rely heavily on our common sense knowledge and reasoning abilities to decipher these ambiguities and fill in missing information. Common sense reasoning has consistently presented unique challenges in NLP research, covering spatial, physical, social, temporal, and psychological aspects, along with an understanding of social norms, beliefs, values, and the nuances of predicting and interpreting human behavior. Models often lack this innate common sense, which hampers their ability to contextualize data coherently, unlike humans who effortlessly understand everyday situations. Recent advancements in large language models, LLMs, have sparked great excitement in the NLP community and beyond, significantly improving a wide range of applications. Building on these achievements, multimodal large language models, MLLMs, have emerged as a key focus in the next wave of AI, speculated to advance towards artificial general intelligence, AGI, which aims to develop AI systems smarter than humans and beneficial for all of humanity. The rise of MLLMs, particularly OpenAI's GPT-4v, Vision, and Google's Gemini, marks significant progress in this area. Among these developments, Gemini emerges as a strong contender to the state-of-the-art MLLM, GPT-4v, specifically engineered for multimodal integration. Its release has sparked constructive discussions about the current level of AGI achievement. In widely used academic benchmarks, Gemini has achieved new state-of-the-art status in the majority of tasks. However, initial evaluations of Gemini, especially when compared to models like the GPT series, have indicated potential weaknesses in its common sense reasoning capabilities, a fundamental aspect of human cognition. But it's important to remember that assessing Gemini's common sense reasoning abilities based solely on the HelloSwag dataset may not fully reflect Gemini's capabilities in this crucial domain. To address the gap in the comprehensive evaluation of Gemini's real-world performance in common sense reasoning tasks, our study conducts extensive experiments across 12 common sense reasoning datasets, covering a wide range of domains such as general, physical, social, and temporal reasoning. We experiment with 4 popular LLMs for the language dataset evaluation, including Llama 2-70B, Gemini Pro, GPT 3.5 Turbo, and GPT 4 Turbo. For the multimodal dataset, we assess both Gemini Pro Vision and GPT-4v. Our key findings are as follows. 1. Overall, Gemini Pro's performance is comparable to that of GPT 3.5 Turbo, showing slightly better average results across 11 language datasets, 1.4% higher accuracy, though it falls behind GPT-4 Turbo by an average of 8.2% in accuracy. Moreover, Gemini Pro Vision performs lower than GPT-4v on the multimodal dataset, except for temporal-related questions. 2. About 65.8% of Gemini Pro's reasoning processes are evaluated as logically sound and contextually relevant, indicating its potential for effective application in various domains. 3. Gemini Pro encounters significant challenges in temporal and social common sense reasoning, indicating key areas for further development. 4. Our manual error analysis reveals that Gemini Pro often misunderstands provided contextual information, accounting for 30.2% of its total errors. Furthermore, Gemini Pro Vision struggles particularly with identifying emotional stimuli in images, especially those involving human entities, which constitutes 32.6% of its total errors. In summary, our contributions are threefold. 1. We provide the first thorough evaluation of Gemini Pro's efficacy in common sense reasoning tasks, employing 12 diverse datasets that span both language-based and multimodal scenarios. 2. Our study reveals that Gemini Pro exhibits performance comparable to GPT 3.5 Turbo in language-only common sense reasoning tasks, demonstrating logical and contextual reasoning processes. However, it falls behind GPT-4 Turbo in accuracy and encounters challenges in temporal and social reasoning, as well as in emotion recognition and images. 3. Our findings lay a valuable foundation for future research in the field of common sense reasoning within LLMs and MLLMs, highlighting the necessity to enhance specialized domains in these models and the nuanced recognition of mental states and emotions in multimodal contexts. Section Summary. Common sense reasoning is crucial for human cognition and involves integrating diverse knowledge to make decisions. However, natural language processing, NLP, models often lack this innate common sense, hindering their ability to understand everyday situations. In this study, we evaluate the performance of Gemini Pro, a multimodal large language model, MLLM, in common sense reasoning tasks across 12 datasets. Our findings show that Gemini Pro performs comparably to GPT 3.5 Turbo in language-based tasks, but lags behind GPT 4 Turbo and faces challenges in temporal, social, and emotional reasoning. These results highlight the need for further development in specialized domains and emotion recognition in MLLMs. Section: Common Sense Overview. Let's delve into the concept of common sense reasoning, a key element of human intelligence that allows us to intuitively understand and interpret the world around us. This is based on basic, often unspoken knowledge and beliefs. For example, if you see someone carrying an umbrella on a cloudy day, you'd probably guess they're expecting rain. Or, if you notice a closed door in a library, you'd infer that silence is needed. In machine learning language models, MLLMs, common sense reasoning is crucial as it allows these models to interact with and interpret human language and visual cues in a way that resembles human understanding. In our research, we delve into various types of common sense reasoning tasks. Here's a brief rundown of each. 1. General common sense. This involves understanding basic, everyday knowledge about the world, like knowing that birds usually fly and fish live in water. 2. Contextual common sense. This involves interpreting information within specific contexts, like understanding that a person wearing a coat and shivering is probably cold. 3. Abductive common sense. This involves coming up with the most likely explanations for observations, like guessing that wet streets are probably due to recent rain. 4. Event common sense. This involves understanding sequences of events and the causal relationships between them, like predicting that eating spoiled food can lead to feeling sick. 5. Temporal common sense. This involves understanding time-related concepts, like the fact that breakfast is typically eaten in the morning. 6. Numerical common sense. This involves understanding numbers in everyday contexts, like knowing that a cube has 6 faces. 7. Physical common sense. This involves understanding the physical world, like knowing that a glass will break if dropped on a hard floor. 8. Science common sense. This involves applying scientific principles in daily life, like understanding that water boils at a higher temperature at sea level than in the mountains. 9. Riddle common sense. This involves creative thinking through riddles, like deciphering a riddle where the answer is a shadow, requiring lateral thinking to associate intangible concepts with physical entities. 10. Social common sense. This involves understanding social interactions, like recognizing that a person is likely upset if they are crying. 11. Moral common sense. This involves evaluating actions based on moral and ethical standards, like understanding that stealing is generally considered wrong. 12. Visual common sense. This involves interpreting and understanding visual information in the context of the physical and social world, like deducing that a person in a photo is likely running a race if they are wearing a number bib and surrounded by other runners. For our experiments, we used 12 datasets related to different types of common sense reasoning. These include 11 language-based datasets and 1 multimodal dataset. The language-based datasets cover 3 main categories of common sense reasoning problems: general and contextual reasoning, specialized and knowledge reasoning, and social and ethical reasoning. For the multimodal dataset, vision and language, we selected VCR, a large-scale dataset for cognition-level visual understanding. We evaluated 4 popular language learning models, LLMs, for the language-based datasets, including the open-source model Llama 2-70B Chat and the closed-source models Gemini Pro, GPT 3.5 Turbo, and GPT 4 Turbo. For the multimodal dataset, we considered GPT 4 Volts and Gemini Pro Vision. Due to API costs and rate limitations, we randomly selected 200 examples from the validation set for each language-based dataset and 50 examples from the validation set for the VCR dataset. During model response generation, we used greedy decoding, i.e., temperature equals 0. There were instances where the models declined to respond to certain queries, especially those involving potentially illegal or unethical content. Sometimes, models provided answers that were outside the scope of the options. In these cases, we categorized these unanswered questions as incorrect. Section Summary. Common sense reasoning is a crucial aspect of human intelligence that allows us to understand and interpret the world based on basic knowledge and beliefs. In this study, we explore various domains of common sense reasoning, such as general common sense, contextual common sense, abductive common sense, event common sense, temporal common sense, numerical common sense, physical common sense, science common sense, riddle common sense, social common sense, moral common sense, and visual common sense. We evaluate our models using 12 datasets that cover different types of common sense reasoning problems, including language-based datasets and a multimodal dataset. We use 4 popular language models and 2 multimodal models for evaluation, and employ accuracy as the performance metric. Section. Prompts. In our study, we use 2 different methods to evaluate language-based datasets. The first method, called zero-shot standard prompting, SP, was used to measure the inherent ability of the models to understand and use common sense in language contexts. The second method, called few-shot chain of thought, COT, prompting, was used to see if the model's performance could be improved. For the multimodal dataset, we used zero-shot standard prompting to evaluate the model's ability to reason using both visual and linguistic information. When we compared the performance of 4 language learning models, MLLMs, on 11 language-based common sense reasoning datasets, we found several important points. Firstly, the GPT-4 Turbo model performed better than the other models on most of the datasets. It performed 7.3% better than the second-best model, Gemini Pro, in the zero-shot learning scenario, and 9.0% better in the few-shot learning scenario. Gemini Pro performed slightly better than GPT 3.5 Turbo, with an increase of 1.3% in the zero-shot SP scenario and 1.5% in the few-shot COT scenario. It also performed much better than the Llama 2-70B model. The COT method consistently improved performance across all datasets, especially in datasets like Commonsense QA, TRAM, and Social IQA. However, all models struggled with certain areas, particularly those involving time, TRAM, and social interactions, Social IQA. For the multimodal VCR dataset, we compared the performance of GPT-4 Volts and Gemini Pro Vision. The VCR dataset consists of 3 tasks: answering a question based on a visual context, Q to A, providing a reason for a given answer, QA to R, and both answering a question and providing a reason for the answer, Q to AR. GPT-4 Volts performed better than Gemini Pro Vision in all tasks, suggesting that it is better at combining visual and textual information to provide coherent responses. However, both models performed worse in the Q to AR task than in the other 2 tasks, indicating that there is room for improvement in understanding the relationship between visual cues and common sense reasoning. We divided 11 language-based datasets into 3 groups and compared the performance of the models in each group. GPT-4 Turbo consistently performed the best in all categories. The Llama 2-70B model performed slightly worse than the other models. Gemini Pro and GPT 3.5 Turbo had similar performances, but Gemini Pro performed slightly better in 2 of the 3 categories. However, it performed worse in the social and ethical reasoning group, possibly because it refused to answer questions that could involve unethical content. All models performed well on social and ethical reasoning datasets, suggesting that they have a good understanding of moral and social norms. However, they performed worse on general and contextual reasoning tasks, indicating a gap in their understanding of common sense principles and their application in different contexts. The models also struggled with tasks involving time and riddles in the specialized and knowledge reasoning category. For the multimodal dataset, we compared the performance of GPT-4 Volts and Gemini Pro Vision on different types of questions. We focused on the Q to A task, which directly measures the model's ability to use common sense in visual contexts. Gemini Pro Vision performed as well as or slightly worse than GPT-4V on most types of questions, but it performed better on questions involving time. This suggests that it is better at recognizing and understanding time-related elements in visual scenarios. Section Summary. In the evaluation of language-based datasets, two prompting settings are used: zero-shot standard prompting, SP, to assess models' inherent common sense capabilities, and few-shot chain of thought, COT, prompting to observe potential performance enhancements. GPT-4 Turbo outperforms other models in terms of accuracy, with Gemini Pro showing slightly better performance than GPT 3.5 Turbo. The COT approach consistently improves performance across all datasets, particularly in domains involving temporal and social dimensions of common sense reasoning. In the multimodal VCR dataset, GPT-4V demonstrates superior performance compared to Gemini Pro Vision, indicating better integration of visual and textual information. Section: Reasoning Justification within MLLMs. We wanted to understand how well multimodal language learning models, MLLMs, can reason, especially when it comes to common sense matters. To do this, we used a systematic sampling approach. We looked at 11 different language-based datasets and evaluated them using 4 different language learning models, LLMs. From each dataset, we randomly picked 30 questions that the LLMs answered correctly and 30 that they answered incorrectly. If a dataset had less than 30 incorrect answers, we included all of them to make sure our analysis was thorough. After picking the questions, we asked each model to explain the reasoning behind its answer. We then manually reviewed these explanations and classified them as either true or false, based on whether they were logically sound and relevant to the question. We found that not every model had 30 incorrect questions for each dataset. In these cases, we scaled up the available data to 30 questions to standardize our calculations. Our findings showed that GPT-4 Turbo performed the best in terms of both correct and incorrect answers, indicating its advanced reasoning mechanisms and its ability to maintain coherent logic, even when the final answers are not accurate. Gemini Pro also performed well, showing good reasoning abilities and a well-rounded approach to common sense reasoning. GPT 3.5, while slightly behind Gemini Pro, still showed competitive reasoning abilities. When we looked at the multimodal perspective, we found that GPT-4 Volts and Gemini Pro Vision, when tested on the VCR dataset, correctly identified the answers about a quarter of the time but failed to provide appropriate reasoning. This suggests that while these models can often determine the correct outcomes, they struggle to understand or explain the reasoning behind these answers. Interestingly, even when the answers were incorrect, GPT-4 Volts and Gemini Pro Vision provided correct reasoning 16% and 22% of the time, respectively. This shows that these models can reason effectively, but this doesn't always lead to accurate outcomes. We also conducted a case study on Gemini Pro's common sense reasoning capabilities. We looked at examples from 4 major categories and evaluated its performance. In the general common sense evaluation, Gemini Pro correctly answered a question from the Commonsense QA dataset and showed an understanding of the unfamiliar nature associated with strangers. In the temporal common sense evaluation, Gemini Pro was unable to provide a definitive answer due to lack of context, highlighting its reliance on specific contextual information to make accurate temporal judgments. In the social common sense reasoning evaluation, Gemini Pro showed a nuanced understanding of social dynamics and emotional motivations but struggled to accurately predict human reactions in complex social scenarios. In the visual common sense evaluation, Gemini Pro Vision was able to analyze a scene involving physical safety and potential danger and make predictions about the potential consequences of actions within that scene. Overall, our findings highlight the advanced reasoning capabilities of Gemini Pro and Gemini Pro Vision, but also point out the challenges in achieving human-like inference. These insights could help guide future improvements to LLMs and MLLMs. Section Summary. To evaluate the reasoning abilities of MLLMs, the authors randomly selected 30 correctly answered and 30 incorrectly answered questions from 11 language-based datasets. They then prompted each model to explain the rationale behind their answers, which were manually reviewed and classified as true or false based on logical soundness. The results showed that GPT-4 Turbo performed well in both correct and incorrect answers, demonstrating advanced reasoning mechanisms, while Gemini Pro and GPT 3.5 also showed commendable reasoning abilities. In the multimodal perspective, GPT-4 Volts and Gemini Pro Vision correctly identified answers but struggled to provide appropriate rationales, indicating a discrepancy between understanding and explaining reasoning. Section: Error Analysis. We've taken a deep dive into the errors made by various models to better understand where they go wrong. We've looked at common mistakes made in tasks that require common sense reasoning, and we've averaged the results across 4 different language learning models, LLMs. We've looked at these models in 2 different scenarios, one where they have no prior examples to learn from, zero-shot SP, and one where they have a few examples to learn from, few-shot COT. We've found that the most common mistake is misinterpreting the context, which happens more often when the models have no prior examples to learn from, 28.6%, compared to when they have a few examples, 23.4%. This suggests that having some context helps the models understand the situation better and make fewer mistakes. The second most common mistake is logical errors, which account for 23.9% of mistakes in the zero-shot scenario and slightly less, 20.1%, in the few-shot scenario. This indicates that having a few examples to learn from helps the models reason more logically. Ambiguity errors, where the models are unsure because the language is unclear, make up 16.2% of errors in the zero-shot scenario and are reduced to 11.6% in the few-shot scenario. This shows that having some context helps the models understand the language better. However, overgeneralization errors, where the models apply patterns they've learned too broadly, increase in the few-shot scenario, 15.6%, from the zero-shot scenario, 11.8%. This could be because the models are overusing the patterns they've learned from the few examples they have. Interestingly, knowledge errors, where the models use the right common sense knowledge in the wrong way, increase significantly in the few-shot scenario, 29.3%, compared to the zero-shot scenario, 19.5%. This suggests that while having some context can be helpful, it can also lead to mistakes, especially in complex or nuanced situations. We've also looked at 2 models, GPT-4 Volts and Gemini Pro Vision, and how they choose incorrect answers in a specific task. We found that the most common mistake for both models is not recognizing emotions correctly, with GPT-4V making this mistake in 30.1% of cases and Gemini Pro Vision in 31.3% of cases. This suggests that both models struggle to interpret emotional cues in visual content. Spatial perception errors, where the models struggle to understand the spatial relationships and arrangement of elements in images, make up 22.5% of errors for GPT-4V and 25.2% for Gemini Pro Vision. Logical errors are also a major issue, more so for GPT-4V, 27.7%, than for Gemini Pro Vision, 24.9%. Context misinterpretation is less common but still a significant problem, with GPT-4V making this mistake in 19.7% of cases and Gemini Pro Vision in 18.6% of cases. These errors show that the models struggle to understand the overall context or story shown in the visual content. Overall, our error analysis helps us understand the specific challenges that LLMs and multimodal language learning models, MLLMs, face in common sense reasoning. This gives us valuable insights for improving these models in the future. Common sense reasoning in natural language processing, NLP, has been getting a lot of attention recently, especially with the advancements in LLMs that have greatly influenced many applications in NLP. However, there are concerns about these models' ability to understand and reason about common sense knowledge. Many studies have been done to evaluate the common sense reasoning capabilities of LLMs, and researchers are exploring different strategies to improve these capabilities. These strategies include using large-scale knowledge graphs and methods of transferring common sense knowledge to give NLP systems a deeper and more nuanced understanding of common sense concepts. Before we can improve these methods, we need to thoroughly evaluate the current common sense reasoning capabilities of LLMs. In our study, we're doing just that by looking at how LLMs, especially the Gemini model, use common sense reasoning in different NLP contexts. In NLP research, it's become essential to pre-train language models on large, varied text datasets. This gives the models a broad knowledge base across many fields. Initially, this knowledge was often used by fine-tuning the models with specific task data. Models like BERT and Roberta are examples of this, being used for tasks ranging from predicting diseases to classifying text and analyzing time series. But with the introduction of GPT-3, the focus has shifted towards more flexible learning methods like zero-shot and few-shot learning, which allow models to adapt to new tasks with minimal data. This shift has led to the development of new techniques to improve the reasoning and understanding capabilities of LLMs, including chain-of-thought prompting, self-consistency with chain of thought, tree of thought prompting, and metacognitive prompting. In our work, we're evaluating 4 popular LLMs for language-based tasks in zero-shot and few-shot scenarios, and 2 MLLMs for multimodal tasks in the zero-shot learning scenario. Our goal is to get a deep understanding of their strengths and weaknesses in various common-sense reasoning tasks. Since the release of the state-of-the-art MLLM, GPT-4v, several evaluations have been done on various tasks, including medical imaging, visual question answering, and video understanding. These evaluations usually focus on either qualitative analyses through example demonstrations or quantitative assessments by analyzing the model's performance across different tasks. The recent release of Google's Gemini has attracted a lot of attention, and early experiments have been done to evaluate its capabilities in both language understanding and the multimodal domain. However, there's still a significant gap in fully understanding Gemini's common-sense reasoning capabilities, a known potential shortcoming since its introduction. In our work, we're doing a comprehensive analysis of Gemini's capabilities in this area, along with comparisons to other leading MLLMs. This will highlight both the potential and areas for further improvement in future research. Section Summary. The error analysis section of the paper focuses on assessing the performance of language and multimodal language models, LLMs and MLLMs, in common-sense reasoning tasks. The analysis reveals that context misinterpretation is the most common error, occurring more frequently in zero-shot settings compared to few-shot settings. Logical errors and ambiguity errors are also prevalent, but the addition of context in few-shot settings helps reduce these errors. However, knowledge errors increase in few-shot settings, indicating that while extra context can be beneficial, it can also lead to inaccuracies. In the evaluation of the VCR dataset, emotion recognition errors and spatial perception errors are the most common, highlighting the challenges models face in interpreting emotional cues and understanding spatial relationships in visual content. Logical errors and context misinterpretation are also significant issues in this context. Overall, the error analysis provides valuable insights for improving the common-sense reasoning capabilities of LLMs and MLLMs. Section. Discussion. In our research, we carried out a thorough assessment of the latest large language models, LLMs, and multilingual large language models, MLLMs, with a special focus on Gemini Pro and Gemini Pro Vision. We used 12 different datasets that test common-sense reasoning to do this. Our results show that while these models have made significant strides in many areas and have shown remarkable results in common-sense reasoning tasks, they still have their shortcomings. They struggle with tasks that require a deep understanding of context or abstract reasoning, such as those involving time dynamics, riddles, or complex social situations. Looking forward, it's important to address these issues to improve the overall effectiveness of LLMs and MLLMs in common-sense reasoning. Future research should focus on improving the model's abilities to interpret and reason within complex contexts and abstract scenarios. There's also a growing need for more comprehensive evaluation metrics and methods that can accurately assess the subtleties of common-sense reasoning in AI systems. These metrics should not only evaluate the accuracy of responses but also their logical consistency and relevance to the context. In conclusion, our research emphasizes that perfecting common-sense reasoning in LLMs and MLLMs is a work in progress. The performance differences we observed among these models reveal interesting areas for further research and improvement. Even though we've made significant progress, achieving artificial general intelligence, AGI, is still a major goal that lies ahead. Our research sets the stage for future exploration in this field, highlighting both the accomplishments and the areas that need improvement in common-sense reasoning within LLMs and MLLMs. However, our study does have some limitations. First, our evaluation heavily relies on the questions and datasets we chose for analysis. Even though these datasets are diverse, they may not cover all aspects of common-sense reasoning. Therefore, the performance and capabilities of Gemini Pro and other models could differ in real-world situations or with different datasets. Second, our analysis is limited to datasets in English, which restricts the applicability of our findings to other languages or multilingual contexts. In these contexts, cultural nuances and linguistic differences play a crucial role in common-sense reasoning. Lastly, our study is a snapshot of a rapidly changing field of AI, focusing on API-based systems that are subject to change. The introduction of new models or updates to existing ones could lead to different performance results, emphasizing the need for continuous evaluation and analysis.